this point you've already seen how to do limits that involve direct substitution, where nothing special is happening. Right? You've already watched this video that had these examples. We saw examples that had domain restrictions and what to do with those. If we weren't at the domain restriction, we saw what to do with those trig functions, and we saw what to do if you can reduce it. Okay, so now we're on to example H here. In example H, I'm going to ask you to evaluate the limit of as the function is approaching 1, and let's say that's a piecewise function. Okay, so here's our piecewise function. Okay, so as we're doing this, because it's a piecewise function, if we think about piecewise functions and the graphs you've done before on those, that's sometimes like you have a piece coming in here and a piece coming in here, right? And they just don't match up, and you'll have what's called a jump discontinuity, where it jumps from one to the other. Okay, but sometimes they do match up, right, for themselves. And by the way, if they match up, we don't care if there's an open circle there. We just care that they're approaching the same value. So let's think about, for this one, what values we're approaching. We're going to do our two directional limits. Whoops. We're going to approach one from the left, and if I'm approaching one from the left, I have to pick which function to use. And it's not like, oh, the left I always use the top and the right I always use the bottom. No, you just look at this right here. This is going to tell you the direction, okay? This right here tells us which direction. Which directional limit to use. Okay, so excuse me. If we're for this, since it's 1 to the left, that means you're a little bit smaller than 1. That means I'm going to use that top function. Okay, so 1 just to the left. Well, if I plug it in right here, right? Because as I look at this, there's no domain restrictions for this. As I plug in 1, I get 1/2 plus 5/2. Okay, I get 3. So from the left, I'm approaching 3. Let's see what we're going to be approaching from the right. From the right, that means I'm larger than 1, so I'm using the other function. And if I do that, I'm going to be approaching 3. So that means from the left and the right, I'm approaching the same value. So if I have it coming from the left, it's approaching 3, and from the right, it's approaching 3. They're going to match up. The directional limits agree, so the general limit exists. So what's the limit for the whole thing? It's just going to be 3. If I do these and these two numbers are different, that means that one side's like let's say this is 3 and that's 2. It means one side's approaching 3 and one side's approaching 2. Then the general limit wouldn't exist because it jumps from one to the other. Okay? Right? In order for a general limit to exist, then the directional limits have to agree. Okay? Plus 4 there. It's minus 4 there. Okay. Okay. So we'll try that one. Right, and be great if you hit the pause button, try it on your own, and then watch my explanation. Okay. So if I'm going to do the left side, which one's the left? That's the smaller than -2. What's smaller than -2? X minus 4 is smaller than -2. I plug it in, I get -6. Okay. What about if I'm bigger than -2? If I'm bigger than -2, it means I'm greater. Okay, that's going to use the -x plus 4. Okay, I plug that in, I get 6. So our two pieces, they both have a limit directionally, right? The left side's approaching -6, the right side's approaching 6, but those two don't match up, so our general limit does not exist. They don't agree. So we would have a DNE for this one, right? Does not exist. Okay, so that's the difference between those two. Right? Okay, so let's take a look at another type. Now here's another specialty one that I was looking at the problem sets you're going to have, and you'd have to be able to do this one. Okay. Okay. So this is the greatest integer function. it also can be written like this. It would be int negative x minus 1. That's basically what's in your calculator if you're going to use, if right? There's an aka for it. It's like this, the greatest integer function. Sometimes it becomes a double bar on the sides. Sometimes they have a bracket on the top and bottom, right? Okay, sometimes it's like this. This all means the same thing. There is a version that tells you to do something different, right? So this one, it always means you round down. Every single time. Okay? Round down to the nearest integer. Okay, if you're already at integer, obviously you wouldn't round because you're already at the integer. So you're just trying to get to an integer. And this kind of makes sense if you're thinking from business perspective, that if you are in the middle of if you're building a bunch of washing machines and you have built 2.6 washing machines, it doesn't matter that you've done 6/10 of the washing machine. How many washing machines do you have? You really only have 2 washing machines. So it rounds down. That would be a case where things would round down. Okay. If this was on top like this, that's something different. This is the round up. Okay, round up is more like when they're charging you when you have a cost of things, like a parking garage. It says for the first 30 minutes it costs this amount. For the next 30 minutes it costs this amount. They're always rounding up. It doesn't matter how close you get. Once you get into that next region, you're rounding up to the next price point. Okay, so that would be a rounding up function in the real world, right? But these are different. This is the round down. This is the round up. Okay, so let's think about what happens. So if I'm just to the right of -2, and for this, right, you have seen the graphs of these, you just may not remember. But so it might be nice. This one might be good to use a table of values. Okay, so I'm gonna do -2, and if I'm just to the right of -2, that's -1.9, right? -1.99 and -1.9999. However many I want to put in there. Okay, we're not going to do it at -2. We don't care what the value is at -2. We're just approaching from the right side. So if I plug in -1.9, that's going to give me positive 1.9 minus 1. So it's 0.9. 0.9 rounds down to 0. Okay. If I plug in this -1.9, I do the opposite. So it's 1.99. Subtract 1. So I get 0.99 rounds down to 0. It doesn't matter how close you are to 1. It's always rounding down. You think of it and you're building that washing machine. If the washing machine doesn't have that last piece, it cannot be sold. It needs to have all of its pieces to be sold. Okay, so if I plug in this, right, -1.999, opposite of it's 1.99999. Subtract 1, I'm at 0.99999. The washing machine's not quite done. It's going to round down to 0. So you can see that from the right, this is approaching 0. Okay. If we had a different direction for ourselves, right, then we would be, we might have a different answer. Okay. Dog has stopped barking. I can play again. Okay. Uh-oh, here he comes. So we might get a moose invasion here in a second. Right. Oh, okay. Oh, here are the dogs.
Sorry.
No, it's okay. Okay, so that was the greatest integer example, which you'll have a chance to work on. Okay. The last type that you're going to see this week on the homework is going to look like this. Okay. And if we're looking at this one, if I can tell that obviously the bottom's going to be 0. All right, so see what the top's going to do. If I plug in 0 here, 4 plus 0 is 4, square root of 4 is 2, minus 2 is 0. So if I just do a straight plug-in, I get 0 over 0. And as I told you, 0 over 0 means you're missing something. You're going to have to reduce. Okay? So for this one, we have to figure out how to reduce this one down. And it's not like the other ones where you can factor it necessarily. So here's what we're going to do. We're going to rationalize the numerator. All right? Remember, rationalizing the denominators in algebra to give it into a better form. Well, we're going to rationalize the numerator. Now, if we rationalize the numerator and distribute out, what's going to happen to the numerator is that we get 4 plus h, and then the middle terms will cancel because I used the conjugate of this. Okay, that's the key when you're rationalizing denominators, and you did that last year, is you use the same exact terms, but you use the opposite sign. And it's going to, when you distribute everything, it's going to cancel out those middle terms. The first term becomes a 4 plus h, middle terms cancel, last term is going to be a minus 4. I'm not going to distribute the denominator because I don't really want to make that mess go into more places. Okay. Well, at this point I can see, okay, now that I've unlocked it, the 4's can cancel, and look, I have h over this mess down here, and the h's can reduce. So what am I left with if I reduce the h's? 1 over 4 plus h plus 2. That's all that's left. Okay, so by rationalizing the numerator, I was able to reduce something that didn't seem like it could be reduced. If I evaluate the limit now, top's just 1. This right here, 4 plus h, evaluates to the square root of 4, which is 2, plus 2. So that's, for my limit there is 1/4. Okay. Now some people say, but that's a domain restriction. Again, remember, limits don't care about domain restrictions. Limits are saying what is the value you're approaching. So just because you have domain restriction, that does not impact the ability to find a limit. Okay. So let's try another one like that. Okay, and let's do, yes, and so you could have an h here, so let's say h is approaching -3, and we'll say that the top here is going to be, no, let's not do 3. Sorry, I'm changing my example that I have here a little bit. All right, so that's a better example. So I'll do h. That's 3. Sorry, guys. Let me just make sure I got this. Okay. Okay, there we go. So, right, this example looks a little different there than the other one. Okay. If we take a look at it, if we plug in -3, the top, this group will be approaching 1, and the square root of 1 is 1, so the whole numerator is going to be approaching 0. The denominator is going to be approaching 0. Okay, 0 over 0 tells us, hey, you're missing something. It can be reduced. Since I have a radical in it, my thought here is to multiply by the conjugate. Notice I'm not changing this sign. That needs to, these two groups need to be the same, so when I multiply them, they just cancel each other out. Okay, so I multiply and I get h plus 4. Middle terms cancel because of the conjugates, minus 1 over, and I'm not going to distribute the whole denominator because if I did, it's not a conjugate, nothing's going to be nicer about it. Okay, so the top here, this is going to give me plus 3. Look at that. So h plus 3 is going to cancel h plus 3, so I'm left with 1 over that group. Okay, limit as h approaches -3. Okay, so that nicely canceled. Well, I go and I plug it in. The top is obviously 1, bottom, square root of 1, which is 1, plus 1, that's 2. Limit 1/2, all set, good to go for myself. Okay, so those are all the different ones you can evaluate there. Use these notes to help you in completing the homework problem set. All right, if you're having trouble with it, all right, I'm going to go through this in Google Meets. It's not a bad idea to look at this once before you come to Google Meets. Wednesday is when I'm going to talk about this. Not a bad idea to review this ahead of time, so when you see it in Wednesday's session, it makes more sense. And of course, I'll have Friday extra help sessions. Thanks a lot and good luck.